Hello, my name is Pei Yun. I'm going to talk to you about our work on safe locomotion planning with self-supervised free-space forecasting. What is a good representation for perception that supports locomotion planning? Here, we visualize a typical urban motion planning scenario from a bird's eye view, where an autonomous vehicle awaits an unprotected left turn. We highlight a candidate plan with a blue arrow, whose endpoint represents where the AV will be in 1 second. An object-centric representation, as adopted by standard perception stacks, focuses on capturing object properties, such as their shape, orientation, and position, both at the current timestamp and the future. Successfully forecasting a future version of an object-centric representation can help identify the potential collision. A free-space-centric representation directly captures the free space of the surrounding scene. Successfully forecasting a future version of a free-space-centric representation can also help identify the potential collision. Forecasting a future version of either representation could help the AV identify a potential collision associated with the candidate plan, however at wildly different annotation costs. Forecasting future object trajectories require a massive amount of object and track labels to train perceptual modules. Instead, in this paper, we explore future free space, whose forecasting can be naturally self-supervised by simply letting time move forward and raycasting future sensor measurements. In a perfect world where we have all the labels for free space versus occupied space, we would directly train a future free space forecaster. However, we do not have such perfect labels because LiDAR sensors are constrained by line-of-sight visibilities. The labels we actually have are visible free space and visible occupied space. Given LiDAR measurements and LiDAR sensor pose, we can perform raycasting to identify them. We also know exactly where LiDAR does not provide labels, that is, the unknown space, visualized here as shadow behind objects. Here's our approach. Given a stream of localized LiDAR sweeps, at any timestamp, we can split the data into past frames and future frames. Raycasting on past frames gives the input, the historical free space. Raycasting on future frames gives the output, the future free space. We train a CompNet that takes historical free space and predicts future free space. We formulate future free space forecasting as a binary classification problem. When formulating the loss function, we ignore voxels in the unknown space. One crucial trick we found to be particularly useful is residual free space forecasting. Since scenes are mostly static, instead of learning a model to directly forecast future free space, we forecast the difference between future free space and historical free space. The residual free space forecasting approach turns out to generalize much better. Here are some qualitative results of free space forecasting. We show 5 frames of input on the left. On the right, we show ground truth at top and predictions at bottom. We see a learned free space forecasting model predicts the turning motion of a vehicle at an intersection. We evaluate future free space forecasting downstream on how it will impact an off-the-shelf planner's performance. We choose a simulated driving benchmark known as CARLA no crash and the state-of-the-art planner on the benchmark known as LBC. When the planner's predicted waypoint is outside the forecasted future free space, we override the control signals with an emergency stop. Here we break down the failure cases on CARLA no crash into timeouts and collisions. By integrating future free space forecasting via post-processing, on most test suites, we reduce the overall failure rates and collision rates dramatically. Because we're not modifying the planner, the agent stalls out when it would have collided. We also explore learning to plan with future free space. Existing works have shown that one can learn a cost function where expert-like behavior emerges as the optimal solution. We show that future free space can provide additional supervision to learning such cost functions. This example shows that free space can provide additional supervision to encourage high cost on objects when learning cost maps. Thank you.